Okay, so today we will start a new topic. It's called regression. In this book, actually, there are three chapters about regression. So, this regression is actually a very broad concept and a very useful. There are lots of useful applications in statistics. But here, of course, we only touch the surface very briefly. But let me just briefly explain a little bit more about it. Usually, we use regression, or regression analysis is called usually, to find out or model the associations between one variable usually denoted by y, which is usually called the response variable, and one or more other variables, usually called explanatory variables. So if you are interested in finding out the relationship between some variable y, the response, or sometimes called the dependent variable, and then if you have several variables that you think probably are associated, you are probably at the beginning you are not sure whether they are really associated or not, but you guess that there may be some association. Right? So there are several variables maybe you all want to consider like that. So those are called explanatory variables. This is also called dependent. These are called independent in that case. Independent. So if you have one variable y and you have several other variables that you want to consider, and sometimes you may want to find out, identify out of which of these variables actually, which variables are actually associated with y. So there are several guesses at the beginning, and then out of those you want to find out which variables are really associated with y. So that is one purpose. And once you do that, then of course you are doing it using a certain type of model. You are modeling y as a function of x's. And then you will have a model. Once you recognize several variables, maybe you identify only one x1 and x2 only as the associated variables, then you will have some model equation saying y is equal to some function of x1 and x2. So once you have that model, then you can use that model to predict the y value for given values of x1 and x2. So those are the main applications. So just to identify variables which are associated with a certain response, and then build up a model and then use the model to predict. But there are various types of regression analysis depending on depending on the type of the response, as well as depending on the function that we consider. So depending on those, there are mainly maybe three types of regression. One is called linear regression. Another is type called non-linear regression. There's another thing called generalized linear. Linear regression, non-linear regression, and generalized linear. So actually linear regression again can be divided into two parts, mainly called simple linear regression and multiple linear. So in this course actually they are just talking about this thing only. But even that, they are not going into a lot of mathematical details, very touching very briefly, but are some ideas which are usually not discussed in other courses, very mathematical courses. Right? So it's a completely different way of explaining these things in this book. So, but most of the applications are in multiple linear regression and non-linear and general classification. But as a building block to understand what we really do, simple linear regression is useful. In a simple linear regression, actually what happens is you have a response y and only one x. You don't have several x's. And then this y is usually a numerical variable, mainly a continuous variable in a simple linear regression. Now I will start with the word regression. Where did this word come from? The regression. Why do we call it the regression analysis? The word regression actually came from the person who used this type of analysis first. So he used the word regression because of some reason, and thereafter everybody is calling it regression analysis. So in his application, this is the one that he used. The term regression was first used by Sir Galton, that is the person who invented the word. He studied the relationship between heights of parents and their children. Right? We looked at this example earlier also when we talked about correlation. So he observed some two interesting phenomena. Now, generally, if you consider the heights of parents, usually there are large number of parents whose heights are close to some average, and there are some parents too short and also too long. So, generally, we can assume that heights of parents are approximately normally distributed. And then, when you look at, so suppose this has some distribution like this for the parents distribution approximately normal. So most of them are on the average range, but few will be too tall or few will be too short. Now what he observed was when they look at the son's heights, the sons whose parents are very tall are on average shorter than their parents. Sons who are very short, who have very short parents, fathers, their heights are on average larger than their father's heights. So what he observed was the second variable. The values of the second variable tends to come towards the mean, right? Because these people are away from the mean, but their sons are going to be little less, so it's coming towards the mean. These parents are very short, but their sons are little taller on average. So it's again coming towards the mean. So he used the word to describe this regression towards mediocrity. That is what he used, regression towards mediocrity. For some reason he used that word, regression towards the mediocrity, and now people use the word regression towards the mean. Mediocrity means the mean in this case. So that's where the word regression comes. It comes towards some direction. So that's where the regression word comes. So after that, everybody is using the word regression. So this is the data actually they had. We will look at this data set little later to explain this. We will discuss about this phenomenon little later in detail. So I will use this data later on. Right. Now, already we know when you have a scatter diagram. Now we are going to restrict our discussion to one y variable and only one x variable. So we are going to talk in a simple linear regression situation. So we are going to assume that our data are in a certain type of football shape, kind of ellipse. And this usually happens if the joint distribution of x and y is a little bit technical, but if the joint distribution of x and y has something called bivariate normal distribution, then usually we have this kind of scatter plot when you take a sample. Now let's look at this example. So in this discussion, actually we are going to assume that throughout this regression chapters, we are going to assume that mainly we have this kind of pattern in our scatter diagram, football shape. The following figure shows the scatter diagram of weight versus height of 471 men aged in a certain age group. Height is plotted on the horizontal axis and weight is on the vertical axis, as I explained earlier. Especially in regression setting, we want to be able to predict something using another variable. When you talk about the correlation, it is not important to talk about which variable is the independent variable and which variable is the dependent variable. You can take any as independent and dependent, correlation will be still the same. But if you want to go further and build up a model and predict, then you have to decide which variable has to be the dependent variable and which variable should be the independent variable. Right? So as I explained in the previous lectures, the variable that you want to be able to predict is the dependent variable, the other variable is the independent variable. So naturally, when you talk about height and weight, maybe one interesting question is, given the height of a person, we may want to predict his or her weight. The other way can also go, but in that case then the dependent variable and independent variable will be other way around. So anyway, if you want to predict the weight using height, weight will be the response y, height will be x. So therefore weight will be plotted in the vertical axis, height will be in the horizontal axis in a scatter diagram. So we are given some summary statistics. Average height of all these people was 70 inches. Their standard deviation was 3 inches. Average weight was 180 pounds. Their standard deviation was 45 pounds, and the correlation is also given as 0.4. So you can see that's not a very strong correlation. But still we have not looked at the graph. So in order to actually interpret correlation, always, as I mentioned earlier, you should better to look at the graph. So we look at the graph. So this is the graph. So we can reasonably assume that the scatter is roughly football shape. Of course, in order to see whether it's a football shape or not, you need a fairly large amount of data, otherwise you cannot see. Right. So they have drawn here two lines. This line is actually the SD line. SD line. That is the line that the data would be if the correlation was equal to 1. If the correlation was equal to 1, then all the points has to be on one line. No? So that is the line, SD line. But in this case, correlation is not equal to 1, it's very low, 0.4. Right. So it's almost a weak association. Right. Now in this case, what we are going to look at something called the regression line. So what regression line means, for example, assume that you consider vertical stripes here. Right? So that means you kind of consider all the weights of people whose heights are a given value. Right? For example, if you consider all the people whose heights are approximately 73, their heights will be in this stripe. And then if you consider all these heights, we can find out the mean or the average of those heights. And if you calculate the average is going to be somewhere here in this case. That's what they have marked, the average So in more technical word, that is called the conditional average of weight given the height is equal to 73. Condition given weight is height is equal to 73. The mean of weight is this number here. If you consider some other value of height, so there is a stripe, there are some numbers for the weight. Their weight average will be somewhere here, and similarly if you consider another stripe. Right. So actually what they have done here is exaggerated a little bit. If you really calculate these averages, they are not going to be exactly on a line. Usually they will be close to a line. So if you can draw a line through those averages, that is what we call the regression line. Regression line. Right. So regression line can be considered as some smooth curve or straight line. If it's a linear one, it will be a straight line. Otherwise, it can be even a curve, which goes through the conditional means of y for different values of x. So that's what you mean by the regression line, and that is what we usually use to predict the y value for a given x. For suppose now we know that when the height is equal to 73 in this sample, there are a large number of different weights, right? But if I take another person, a new person whose height is 73, and suppose I don't know, suppose somebody told me that there is a person whose height is 73, but we don't know his weight, right? My prediction of his weight will be this number here. So that will be my prediction, right, using the regression line. So there will be obviously some error. His actual weight can be somewhere here or somewhere here. My prediction is there, so there will be some error. That's called the prediction error in that case. Right. So as I mentioned earlier, SD line is the dashed line in the graph. That is the line where the points would be if r is equal to positive 1 or negative 1. If r is equal to negative 1, it will go down, but again the points will be on the line. But in this case, r is not equal to 1. So therefore, on average, the people will be on the regression line. So this is what actually happens. If someone is 1 standard deviation taller than the average height, his weight is going to be only, actually what happens is, let me go to this graph. So if r was 1, all the points will be here, and this is actually the average height and average weight. The both lines actually go through the average point, average x and average y point. There will be both lines go through that. And if r was 1, when I go from here 1 standard deviation of height, weight will be 1 standard deviation of weight, and then point will be